Okay, so I am going to speak about work which I have done with my collaborators at University in Palermo, Giorgia Belomonte and Professor Camillo Trapani. These are results which will soon appear in a paper in Banach Journal of Mathematical Analysis. So I want first to say a few words on the motivation for this. We are interested in representations of positive maps between C-star algebras and more general positive maps. Why that? This is because a positive and completely positive maps it is known that they have important role in quantum information theory and theory of entanglement and so on. So it was a long time ago that a Stein-Spring theorem appeared regarding representations of completely positive maps, but so far there were no many results on representations of positive maps. So we were trying to obtain representations of positive maps by generalizing GNS construction. And there, in order to obtain such representations, you need various generalizations of Cauchy-Schwarz inequality for such maps. And that is how my talk now will be related to generalizations of the Cauchy-Schwarz inequality. And we are now not going to study positive maps just from a C-star algebra into another C-star algebra, but we are going to study positive maps from a C-star algebra into an ordered Banach bimodule, which means that the bimodule has a cone. Okay, so now, as I said, the motivation comes from representation theory and applications in quantum information theory. Now I can start to define the class of Banach bimodules which we are going to study. So I is a Banach bimodule. If it is a Banach bimodule over a star algebra I0, then we say that I is an ordered Banach bimodule if it contains a positive or closed cone. And we know what it means, definition of a cone. These properties have to be satisfied for this subset K. If those are satisfied, then this is a cone. But we require another additional property. Since this is now a bimodule over a star algebra, we require also that Z star KZ is a subset of K for every Z in the star algebra I0. And we are going to study some concrete Banach bimodules, so I need to fix also some notation. Omega will denote a compact Hausdorff space, and as usual, C omega is the commutative C-star algebra of continuous functions on omega, and N omega is its dual. It is, in fact, the Banach space of all complex radon measures on omega. So now let us first present some examples of such Banach bimodules which we are interested in. The first example is non-commutative LP space. What does it mean? We take a von Neumann algebra M, and we take a row of faithful semi-finite trace on M, and then we consider this standard LP row, non-commutative LP space. In fact, it turns out that this is a Banach bimodule over it is in fact just a star algebra, not Banach star algebra, but a star algebra I0, L infinity row intersected with LP of row. L infinity row here is simply M, so we intersect M with this space here, and then it becomes a star algebra, and this is then a Banach bimodule over this star algebra. Of course, if the trace is finite and not just semi-finite, then in fact this I0 will be the whole M. So then it is a Banach star algebra, and then this is a Banach bimodule over this. Another important example is the space of operators. So if C1 is a unital C-star algebra and Z is some other ordered Banach bimodule, then we can consider the space of bounded linear operators from C1 into Z, and then it turns out that this is also a Banach bimodule over C1. The multiplication is defined in a natural way here. By the way, this is a misprint. It should be Z, not C2. So we can define module multiplication, and this becomes then a Banach bimodule over C1. And what is the special case? The special case is, for example, if you let Z simply be the field of complex numbers, then this becomes the dual of C1. And even more special case is if C1 is the C of omega, then the dual of C of omega is M of omega, the space of Radon measures. And also we are going to consider Hilbert module, the standard Hilbert module L2 over this commutative C-star algebra C of omega. This Hilbert module is not just a Hilbert module and Banach module, more general, but in fact it is even a Banach star algebra over itself. Okay, so now this is just to give an intuition what kind of modules we are studying. And now we can move straight away to the main result. So we want to obtain Cauchy-Schwarz inequality for positive Sesky linear maps, taking values in such Banach bimodules. And then we managed to distinguish several cases where this Cauchy-Schwarz inequality holds for some particular Banach bimodules. The most simple case is the Lebesgue space L2 of omega or the Lebesgue space L1 omega. Of course, they are bimodules over this C-star algebra. But now there is another more interesting case. We can let I be the space of bounded linear operators from a von Neumann algebra M into the space of trace class operators on a separable Hilbert space H. So this is in fact a module of this kind here, as I said, and of course it is a bimodule over M. And if you take any positive Sesky linear map taking values in this module, then the Cauchy-Schwarz inequality holds. Of course, I should say what is the cone here. Of course, the cone here are positive operators. What are positive operators? Those operators which map the cone in M, the cone of positive elements in M, into the cone of positive elements in B1 of H. Natural definition of cone. Okay, so it is important to say that here we consider arbitrary positive Sesky linear maps. So there are many papers on generalizations of Cauchy-Schwarz inequality for some concrete maps. Here we study a general positive Sesky linear map, but we require that it takes values in this Banach bimodule. Another kind is if you take, this is in fact a special case of this one, if you simply consider the dual of M. And as I announced also, if you consider the dual of C of omega, M of omega, also in this case, any positive Sesky linear map taking values in M omega satisfy Cauchy-Schwarz inequality in the norm. There are more cases. This is the same theorem. So there are more cases. You can consider the space of bounded linear operators from M into M of omega, where the operators from a von Neumann algebra M into the space of Radon measures on omega. And you can also consider the Banach bimodule, the space of bounded linear operators from C omega into another commutative C-star algebra of functions. You can also consider the situation of bounded linear operators from a von Neumann algebra into C omega. And then you can consider the space which we were also very interested in, the space non-commutative L1 space. Then it becomes, as I said, a Banach bimodule or the respective von Neumann algebra. And you can also consider the situation of bounded linear operators from a von Neumann algebra M into the dual of another von Neumann algebra. And finally, as I announced, you can consider this standard Hilbert module over C of omega. So in all these cases, given any positive Sesky linear map taking values in these modules, the Cauchy-Schwarz inequality in the norm holds. And now you can see what happens here if you take a non-commutative L1 space, but you assume that your map phi takes values in M intersected with this. Then, in fact, you will have a map which goes into a C-star algebra, a positive map which goes into a C-star algebra, and then you come back to this initial story of positive maps between a C-star algebras. Before saying something about applications, I want to say something about some corollaries of this theorem. So far, we consider it Sesky linear map, but we can easily pass to linear maps. Okay, so let now A be a unital star algebra, and let omega be a positive linear map from A into this Banach bimodule, one of these Banach bimodules in this theorem here. Then one can prove this inequality here for all A and B in A. So one can recognize this as Paulsen's modified Cadison-Schwarz inequality. So Paulsen had something like this, but for two positive maps. And now we do no longer require that a map is two positive. We just require that a map is positive. But another limitation which we put here is that we consider some concrete Banach bimodules here. And this is easily proved simply by defining Sesky linear map in this way here and applying the theorem above. Another application is if you pass to infinite sums. So then you can consider the sequence of positive Sesky linear maps taking values in I, where I is one of these Banach bimodules considered above, but not all Banach bimodules considered above, but only those having the norm which is order preserving. In particular, L1 of non-commutative L1 space is example of a such module. So we need this additional assumption that the norm is order preserving, and then if you have this, then what happens that if you have a sequence is xn and x tilde n in x, such that these sums are convergent in I, then you can obtain this generalization of Cauchy-Schwarz inequality. Okay, so so far we speak about inequalities and applications, but I want to say something about applications to representation theory. Or how does it work? Well, the question is, why do we need these Cauchy-Schwarz inequalities? Well, it is because we want to obtain representations in certain spaces, and we want that these spaces have a norm induced by phi. And in order that the phi induces a norm, we need Cauchy-Schwarz inequality. How does it work? Well, we want to have an I-valued inner product. And it can be induced by an I-valued faithful positive Sesky linear map. And it is simply defined in this way here. Of course, now you need that your Sesky linear map is in addition faithful. And then you can define, if you take this as an inner product, taking values in I, you can define a norm in this way here. Why is this a norm? Well, because the triangle inequality is satisfied. And why is the triangle inequality satisfied? Simply because of the Cauchy-Schwarz inequality in the norm for this Sesky linear map. So this is the reason why, this is how we were motivated to study Cauchy-Schwarz inequality in the norm for such maps because we want these maps to induce such a norm. And then when they induce a norm, we have a space which we call BI space. A space which is complete with respect to this norm is called a Banach space with an I-valued inner product, or for short, a BI space. Notice that this is in fact an extension of the notion of a Hilbert C star module, because for Hilbert C star modules, you have this inner product, but it takes values in a C star algebra, and also it has some additional properties that it is linear with respect to this C star algebra. And here you do no longer have this property, and you have an inner product taking values in a Banach, more general Banach bimodules. So this construction is in a way extension of a construction of Hilbert C star modules. And of course, there are ways to bypass this requirement that phi is faithful. So if phi is not faithful, you can consider this subspace, which is in fact equal to this subspace by Cauchy-Schwarz inequality, and then you can consider this quotient space, and then you can equip this quotient space by this norm here, because this is then a norm on this quotient space. It is just the same in norm on X, but it is a norm on this quotient space. So there are ways to bypass this requirement on faithfulness. And I do not have very much time left, but I just want to say what is the main application. So we want to study representations, as I said. So if C is a C star algebra with unit, and you have a BI space with this inner product, then a linear map pi from C into BK is called a bounded star representation if this property is satisfied and if this property is satisfied for all AC in C. And now you can ask me, what is the notion of the adjoint in this space B of K? Well, this is similar as for Hilbert C star modules and more elementary for Hilbert spaces. The adjoint is simply, it can flip out here. So Txi is equal xt star I for all xi in K. As we know, for Hilbert C star modules, not every bounded linear operator does need to have an adjoint. This is not the same as for Hilbert spaces. And as you can guess, this should be the same situation here. We do not always have a joint, but in fact, this map has this property that if you apply P to A star, then you always get an adjoinable operator, and its adjoint is given in this way here. And the representation is cyclic if it has this cyclic vector that PC is dense in K in its norm topology. This is just the standard. And we also require additional property that our map is left invariant. It means that f of ACD is f of C A star D for all ACD in C. And it is induced, in fact, by linear maps when it is defined in this way here. And then we have a representation. So we are in the position to represent any left invariant positive Assesky linear map from a C star algebra, C times C, into such Banach bimodule I. It is given in this way here, and it is represented in the space. It takes values in the space of bounded linear operators on K phi, where K phi is as such BI space, which I was speaking earlier about. So it is defined in terms of this inner product, and this representation is bounded cyclic and also satisfy this for all A in C. So in other words, we give an explicit description of such positive Sesky linear map, and we can easily then pass to positive linear maps. And they have a representation of this kind here, where this is a cyclic vector, and it is unique up to unitary equivalence. And I believe that I spend my time here. Here are the references. These two papers are already published with my co-authors, Belomonte, Trapani, and Bogdan Đorđević. And now, as I said, these results will appear in Banach Journal of Mathematical Analysis. And here are some other important references. in particular Steinspring's result, Sturmer monograph on positive maps, Paulsen's monograph, and we have also this nice monograph on trace inequalities, and so on. And I believe I can maybe stop here. I believe that I spent my time now. Thank you for attention.